Hello, we're going to talk about I'm just going to quickly finish going through this quiz with you. Um, so, I think we went through this one, but let me make sure I can write on here. Okay. The volume of distribution of a drug given 400 every 12 hours. So their dose rate is 800 milligrams per day. Has decreased. So there's a decrease in the volume. What would you do to ensure that there's no change in the CSS average or peak to trough ratio because of this volume change? Well, would you expect there to be a change in CSS average? Well, CSS average is determined by bioavailable dose rate over clearance. And what we've had here is a decrease in volume. So would we expect a change in CSS average? No, because volume does not determine this. So no change in dose rate. How about dose interval? We need to look at peak to trough ratio. What determines peak to trough ratio? Well, we know K and tau. We control tau. But what about K? K is determined by clearance and volume. What's happened here? We've had a decrease in volume. So we're going to see an increase in K and a decrease in our half-life, aren't we? So the slope is going to get steeper. Our peak to trough ratio is going to get larger. So we're going to need to decrease our dose interval. We're going to have to give it in smaller birdie bites. Right? So if we use this half and two-fold thing, we're going to make no change in dose rate, but we're going to decrease tau. So our dose rate now is 800 milligrams per day. Our tau is every 12 hours, so we're going to go to every 6 hours, which is 4 doses. So how many times does 4 go into 800? So we would give 200 milligrams every 6 hours. Giving the same daily dose, but now giving it in 4 doses rather than just 2. How about drug ABC? If we give drug ABC, which we know is highly bound, it's 85% bound, isn't it? If our fraction unbound is 0.15. And it's highly bound to AAG, so it's a substrate for AAG. It's also got a bioavailability of 0.76 and an FA of 1. So if our patient is a burn patient and has an increase in AAG for a drug that's bound to AAG is going to mean there's more of that binding protein around. So is the drug going to become more bound? Yes, it's going to become more bound. So the fraction unbound will decrease, right? Because the fraction bound has increased. So if we have a decrease in fraction unbound, what's going to happen? Will it alter bioavailability? Well, bioavailability is equal to FA times FG times FH, right? Will changes in fraction unbound affect any of these? No. So we'll see no change in bioavailability. How about volume of distribution? Will a change in fraction unbound determine change volume of distribution? Well, VSS is equal to VP plus VT times the fraction unbound in plasma over the fraction unbound in tissue. So what's happened here? We've had a decrease in our fraction unbound in plasma. If I don't have a P or T here, it's a P. I'm just lazy. And we use the fraction unbound in plasma a lot more. So we're decreasing fraction unbound in plasma, which will decrease this whole thing, won't it? So we're going to see a decrease in our volume. Next, drug V is also an AAG substrate that's being given by IV bolus to your patient when he experiences a heart attack, which again increases AAG. Since it's a AAG substrate, the fraction unbound is going to decrease for drug V when they have a heart attack, right? So what's that going to affect? Do we want to make a change in dose rate? Well, we can see here too, this is our original line, and then after an MI, it looks like this. What's happened? We've had an increase in our K, right? Well, what could that be due to? What determines K? Clearance and volume. Well, we know that the fraction unbound decreases due to the increase in AAG, and that will cause the whole volume to decrease, which will increase our K, right? Our half-life will decrease, and therefore we're going to want to decrease our tau, aren't we? Oops, I skipped the dose rate, but we know we want to decrease tau, so we're going to decrease our dose interval. How about dose rate? What determines dose rate? Well, we need to look at our CSS average, don't we? Bioavailable dose rate over clearance. Are any of those determined by volume? No. And does it look like the actual area under here is different? No, they should be the same. So dose rate should not change. Gave myself an extra slide there. Okay, your patient weighs 115 kilos and is taking drug A, which is 84% bound in the plasma to albumin and 22% bound to the tissue. So it's more highly bound in the plasma, right? Which is the smaller compartment, so we expect a relatively small volume of distribution. Drug A has a KD of 11.4 for albumin, and drug B has a KD of 2.1. So which one has the stronger affinity? The lower the KD, the stronger the affinity, so drug B is going to win the love triangle, isn't it? Drug B is going to displace drug A from the protein binding site. So what's going to happen is the fraction unbound for drug A will increase, right? Because it's been freed from the protein because drug B came and took its place. All right, so what is the VSS of drug A? Well, remember, VSS is the plasma volume plus the tissue volume times the fraction unbound in plasma minus the over the fraction unbound in tissue. So we know the fraction bound is 84%. So what's the fraction unbound going to be? 16%, right? We'll put that in the numerator there. And the fraction bound in tissue is 22%. So what is the fraction unbound? 0.78, right? And then, so that's going to be our fraction unbound in plasma over fraction unbound in tissue comparison there. Our VT is going to be 0.56 times his weight, which is 115 kilograms. So this whole thing together plus 0.04 times 115. Sorry, this is getting pretty messy. Get my calculator out. Okay, so 115 times 0.04 is 4.6, so that's going to be 4.6 liters, and 115 times 0.56 is 64.4 liters times 0.16 divided by 0.78 plus 4.6. So I got a VSS of 17.8. It was 17.81, so rounding to the nearest tenth is going to be 17.8 liters. Would you likely need to change the patient's dosing regimen of drug A due to the addition of drug B? Well, we know there's been a binding change, right? So let's do this part first and then we can come back. So do you want to change the dose rate of drug A? Dose rate is determined by CSS average, which is bioavailable dose rate over clearance. None of these are volume, so I'm going to say no change. How about dose interval? Dose interval, we need to look at K, clearance over volume. If the fraction unbound has increased, that's going to increase our volume. So we're going to see a decrease in K and an increase in half-life. So we're going to want to increase our dose interval to follow our half-life. Or you want to think about, if we have a decrease in K, the slope of our line has gotten flatter, hasn't it? So our peak to trough ratio is less. We can extend our dosing interval or increase our dosing interval. Okay, I guess I could have spread that out a little bit instead of jamming it all on there. Okay, what's the relationship between VSS and fraction unbound in tissue? VSS is equal to VP plus VT, fraction unbound in plasma over fraction unbound in tissue. So these two components here. Well, which one's the dependent? Does the volume distribution determine binding? No. Binding determines the volume, right? So the independent variable is going to be your fraction unbound in tissue, isn't it? So if we're going to draw the relationship, the fraction unbound in tissue goes on the x-axis where the independent variable goes. And so VSS must be the dependent variable, which makes sense, right? Because the volume is determined by tissue binding. Tissue binding is not determined by the volume. The volume is the result, isn't it? So VSS is the result. So now what I do is I say, okay, as fraction unbound increases, so as fraction unbound in tissue increases, what's going to happen to our VSS? It's going to decrease, isn't it? So as our fraction unbound increases, our VSS decreases. This is an inversely proportional relationship, right? As the fraction unbound increases, which means it's less highly bound in the tissues, our volume is going to get smaller because it can move into that smaller compartment. Okay? All right.